All right, here we are. It's tax day, actually, 4/15/21. But I think tax day was moved to June or something because of COVID. But traditionally, the 15th of April is tax day. And we're talking about antiderivatives. So we're starting to go into Calc 2 territory. And I'll begin with a question. So generally, here's my motivation. We can do a motivation or recollection. Okay. If I give you a function f of x, say something fun, 2x minus 1, and I say, okay, hold on, let me get this right. F of x equals x squared minus 2x. And I say to you, what's the derivative of this? You say, okay, I take the derivative, I use the power rule, and I get 2x minus 1. And that's what we've done all semester with different forms of things, with chain rule, product rule, quotient rule, all that kind of stuff. So what we ask in Calc 2 is to go the other way. So that's why it's antiderivative. So we're going this way. So here's the question. If I give you a function f of x, can you find a function capital F of x such that the derivative of this thing is f? If so, cap f of x is an antiderivative for little f. Right? And when I said and, this guy, because they're not unique. And I'll explain why in a second. So here's a fun little example, just to use the one above. Let f of x be 2x minus 1. Find some function f of x such that the derivative is 2x minus 1. Okay, well, we just showed x squared minus x works. I did a mistake here. Hold on. This is supposed to be, I'm sure you all saw this and you're wondering what the hell is going on. This is supposed to be x squared minus x. Sorry about that. And so that works, right? But, okay, here's another one. That works. If you take the derivative, you get 2x minus 1. That works. If you take the derivative, you get 2x minus 1. This works, right? There's infinitely many. In fact, there's a whole family of functions. So the family of functions f of x is the family of antiderivatives. And all of these are exactly the same in the sort of x parts, right? This has got to be the same because we need to get 2x minus 1. And what changes here is the constant that we add to the end. So when you find an antiderivative, you slap on a constant because the derivative of a constant is 0. So it's going to be f of x. How can I write this? Well, I guess it's f of x plus c. We'll just write it that way. But f of x involves c. The notation's a pain, and this C we'll show later on is called the constant of integration. And if you're given some initial conditions, you can actually solve for it. And so all we're doing now is undoing differentiation. So we're going anti, and each time you pick up a constant, and these constants up here are, this is 0, 1, -7, pi, or just C. Okay. All right, and this has a notation, this family of notation. This family of antiderivatives uses this sign. This is called an integral sign. This is called the integrand. And this is a differential. Next week I'll show you where the dx comes from. And this equals f of x plus c. And this collection of antiderivatives is called the improper integral of little f of x with respect to x. Okay. And so integration is the reverse of differentiation. And all the rules of differentiation hold as well. So if you take the integral of some constant times f of x dx, the constant comes out front and it just multiplies. Right? Or if you take an integral of two functions that are added together, it's just the sum of the, or the difference of that, just like derivatives, right? Sum and difference rule and that. All right, so let's get into this for real. So over here I have some differentiation rules. Yeah, no, I don't want to do it that way. It's too formal. We'll get formal next week. This is supposed to be sort of an informal introduction. Before we had what f of x equals get my head on straight here. F of x equals 2x minus 1, and the antiderivative was x squared minus x. And so to go from here to here using the derivative, we have a power rule, right? And so we also have a power rule to go from here to here. But the power rule is a little different. If f of x is x to the n, then its antiderivative, you take this number, you add 1 to it. So when we take the derivative of something, you subtract 1. But when you take the antiderivative, you add 1, and then you add out front, you multiply by 1 over that thing you added. Right? And n can't be -1. Otherwise, this is undefined. So this is the power rule for antiderivatives. Okay, and you always have your plus c out there, right? So if f of x is 2x like above, then there's a 1 here. So you add 1 to that, and then divide by 2, so you get x squared. Right? Just to use different notation, if you have x to the fourth, right? You take x to the 4 plus 1, and you put 1 over 4 plus 1 out front. So it's 1/5 x to the 5th plus a constant, right? So when you differentiate, you subtract and multiply, and when you integrate, you add and divide. Separation of church and state. Okay. And this works with fractions, so we have, let's say 2/3 here, right? So cap H is 2/3 plus 1, and we have 1 over 2/3 plus 1 out front here, plus C, and this equals x to the 5/3 with a 3/5 out front plus C. Yeah. And what if Hij(kx), what if we have x to the -1, right? Well, if you take kx of this, you have x to the -1 plus 1, which is 0, and you have 1 over 0. So this is undefined. We said that above here. And can't be -1. But if you think about this for 1 second, x to the -1 is 1 over x, and the derivative of ln is 1 over x. So the antiderivative is the ln of x plus c. And we always put absolute value bars around because you can't take the ln of a negative number. Okay, let's just keep thinking out loud, or I will. What if L of x is cosine of x? Which function has the derivative of cosine? That's sine, isn't it? Right, because L prime of x is cosine. Ln. What if I have sine? Then we need a negative out front, right? Because the derivative of cosine is minus sine, and a minus times a minus gives us positive. So we need n now, little n. So n sub x, let's say n sub x is secant squared x. So what function has a derivative of secant? Well, that's tan. Right. What else? P. Let's say I have e raised to k times x, where k is some constant. Then cap p is 1 over k e to the kx. That's because when you take the derivative of e to the kx, you get a k out front, and those k's cancel and become a 1. See what else here? pq. What if q of x is 1 over 1 plus x squared? What function has this derivative? Well, it's tan inverse. Right. And so let's do this. What if we had 1 over this guy? This should be little r. Little r of x, 1 over this, and if you remember, the so the derivative of what sine inverse equals that. And so what if we had, all I'm doing is thinking backwards here. What if I had 1 over x times the square root of x squared minus 1 for my s? What's CapX? What's secant inverse? All right, so we're just going backwards here. And there's a nice table in your book that has, where is it here? I'm just looking at it. There it is. Yeah, that's got, so it's got cosecant square, which I'll never ask you for, and secant tan or cosecant cotan. I won't ask you those, but all the other ones I might ask. So 5, 6, 7, and 13 you can ignore. The other ones are fair game. And I just sort of did all of those for you. And yeah. So now we have antiderivatives, which are super cool. And everything you need to finish chapter 4. So tomorrow's workshop will be, we'll do one or two, probably do one Newton's method, and then the rest will be working on this antiderivatives. And you can see how important your book and the world thinks this is, because if you look at the exercise set for 4.8, there are 32 problems. Okay, it's one of the biggest sections I've ever seen in this book. So I'm going to assign all 132 problems for Monday. Just kidding. It'll be about 10 from here, and we'll do some of them in class on Friday. All right, see you in a minute.